And they did the liposuction to them, and the women were randomized into just observation or have the liposuction. And of course, when you have liposuction, because they sucked a small amount of fat, you lose a small amount of weight. So those people lost about 2 kilograms. These women lost 2 kilograms by doing a liposuction on their upper thighs and lower abdomen. But what happened after 12 months later? They started from here, they lose the weight, and almost 12 months, they're almost back at the same level they started their weight, despite the fact that we took that fat surgically. But the interesting part comes here, that where did that increase in weight, where did it come from? Where did the fat deposit itself? So we can see that there is certainly increased fat in the thigh itself, or the lower abdomen where they took the liposuction from. But really the most increase coming from abdominal fat on MRI and DEXA, and most of that was visceral fat. So what's interesting here is that you took subcutaneous fat from the upper thigh or the lower abdomen, the body itself compensated by regaining that fat mass within 12 months, but actually putting it even in a worse place, in the visceral fat, rather than the subcutaneous fat. So the body knows how much fat you have, and will try to maintain it. Rightly or wrongly in the wrong place, but still try to maintain the fat mass. So in this study, they followed up people longitudinally for a long time, for more than 40 years. And this was actually a cancer study, so they wanted to see who will develop cancer and try to predict who will develop cancer. But if you forget the cancer bit and you look what happened to their BMI trajectories over 40 years. So this is a lot of people, more than 100,000 people, where you can see that over 40 years, you can define 4 trajectories. There are people who started with normal weight, and they gained weight over 40 years, but they still remain in normal weight. There are people who start with normal BMI, and after 40 years, they end up with overweight, just about. There are people who start with overweight, and they end up having obesity. There are people who start with normal BMI, and have obesity by the end of the year, 40 years follow-up. And there are people who start with overweight and end up having obesity. So if we look at the total amount of weight gain they gained over these 40 years, we can actually model how much was their calorie excess over those 40 years period. So just to put it in context, in this group of people who were overweight and developed obesity after the end of the follow-up, they gained 40 kilograms over 42 years. That's less than a kilo a year, or just about a kilo a year. And if you model that and basically calculate how much the excess calorie intake every day was, that's about 20 calories excess per day. So I would like to ask, how many of us think they can calculate 20 calories excess per day? It's so difficult to calculate 20 calories excess per day. You want to do it willingly. How can you actually calculate 20 calories excess per day? If you are in the other group that moved from the normal BMI to obesity, then you gain about 15 kilograms over 42 years, and that's 7 calories a day. That's even lower. So it's difficult to see how this can be under conscious control. With that minute amount of calories, any small piece of chocolate will have calories a lot more than this number. So that will not be even equivalent to one small bite of bread. And interestingly, again, just to support the concept that the body self-regulates itself, in this study, they followed up people on daily basis. I don't know how they found these people, but they found people who recorded their energy intake on daily basis. And then they summarized it on a week level. They averaged it on a week level for a whole year. And those people had to have weight stability. And that's what they had. So they had people who started with 62 kilos, and over 1 year, they remained at 62 kilos. No weight increase, reduction in this group of people. Look at the green color. That's their energy intake from week to week. What you see is a huge variation in energy intake. Look at the numbers. You can be from low as 1,000 calories a day up to high 3,500 calories a day. So the average daily or weekly calorie intake vary hugely in these individuals, with some variation in the energy expenditure, which is the gray color. So the green is energy intake, the gray is energy expenditure. What is the result? The result is weight stability. So whatever they are having here, whether they have a high day or a low, whether they have a high few days and then low few days, the body is self-regulating itself. You eat more one day, the body will eat less the other day. You eat more 1 week, it will eat less the other week, to actually keep that weight maintenance. So these are people who are able to maintain their weight for a long time, and their body can regulate, despite a huge variation in energy intake from day to day, it can actually still maintain their weight, and not with a huge adjustment of energy expenditure. So there is a powerful mechanism that controls our weight. And that mechanism is in the brain. We have 3 different pieces of centers that control our appetites. One of them is the homeostatic system, which is mainly sitting in the hypothalamus and the brainstem. And this is receives signals from the periphery, some satiety hormones like GLP-1 and others, some adipokines like leptin, hunger hormones, and also neural signals that tells the body about how much energy levels are there is inside the body or how much is fat mass. But that homeostatic system doesn't work on its own. It also communicates with other systems in the body. It's called the hedonic system. And the hedonic system controls the energy, the pleasure of eating. It controls both the wanting, which is via dopamine, or the liking, which is via cannabinoid. Both of these systems talk to a higher level. So just remember, these are actually all subcortical areas. None of these are actually cortical. All these centers are subcortical. So they are not under your conscious control. This is all subcortical. But these 2 levels talk to the top level, which is your executive function, which is part of it is cortical. So those 2 tell the body about how much energy stores there are, how much their hedonic aspects related to food. They feed it to the executive function that makes the decision about eating or consuming energy. If these 2 are overactive, i.e. they are bombarding the executive function, the cortical aspect, if they are bombarding the executive function with signals saying, you don't have enough fat, even though you might do actually have enough fat on the body, but they will tell the brain that you don't have enough fat, and the hedonic system keep bombarding the executive function to eat, then the executive function basically will just be faced by an overwhelming signal system saying, eat, eat, eat. And then they eat, and they gain weight. On the other hand, if you put a brake on the hedonic and homeostatic systems, and they start less bombarding the executive function with signals, then the executive function has a better chance of making the right decision for your mass. And that's what happens in obesity management. Lifestyle interventions try to strengthen your executive function daily by making that willpower energy restriction more. The problem with this is that it can work for a short period of time, but eventually the executive function get tired and fail with the increasing signaling from the homeostatic and the hedonic subcortical systems. While bariatric surgical drugs work at this level, they reduce the homeostatic signaling, they reduce the hedonic signaling, and then they allow the executive function actually to make the right choice and the right decision related to the eating behavior. So now we move to the next part of the talk, which is, let's focus a little bit on GLP-1 in terms of obesity management. And yeah. Here we go. So what is GLP-1? Glucagon-like peptide 1. It's a naturally occurring hormone. It's a peptide. It has 31 amino acids in it, and that's how it looks like. It's secreted from many areas, but mostly from the L cells in the gut. But also, there is a lot of GLP-1 secreted in the brain as a neurotransmitter. One of the features of naturally occurring GLP-1 that it has an extremely short half-life because it gets degraded by the DPP-4, and that's why you have DPP-4 inhibitors in the management of type 2 diabetes. So it only lasts in the circulation 2 minutes, and it almost totally destroyed at the endothelial cell levels, which collects the blood from the gut. And if you wonder how does it actually then get to the brain if it destroyed all of there, and how does it do its function, interestingly, a lot of it actually bypass the portal circulation and goes by the thoracic gut into the aorta straight away. But that's a different talk. And what does GLP-1 do? How was GLP-1 discovered? GLP-1 came, and incretin came into attention by noticing that if we give people oral or intravenous glucose challenge, we get the same glucose levels. But when we look at the insulin levels, we see a huge difference in insulin levels in response to intravenous and oral glucose load. So the insulin levels are far higher when the person given an oral glucose load compared to the intravenous load. And that difference is driven by incretins, mostly by GIP, but also by GLP-1. And that's how incretin effect was defined. And that's why incretin effect initially came as the diabetes management, because they can see the difference impact on improving beta cell function.